Tonight, before you fall asleep, do something small. Reach over and turn on the lamp beside your bed. Watch it come on. Notice how there is no delay, no flicker, no hesitation. It simply works. And then, if you are the kind of person who thinks about things a little too much before sleeping, consider this. That lamp is connected to a system so large, so interconnected, so quietly dependent on thousands of moving parts, that keeping it running in peacetime is already an engineering achievement. Now imagine someone is trying to destroy it, every night, with bombs. That is not a hypothetical. That happened. And the lights, for the most part, stayed on. This is a story about one of the least celebrated victories of the Second World War. Not a military victory in the conventional sense. No single general won it. No famous regiment held the line. It was won by engineers in overalls working in the dark, by line crews driving toward fires that other people were running away from, by control room operators making split-second decisions about where to redirect power as the bombs were still falling, by a grid that, almost by accident, had been built in a way that made it extraordinarily difficult to destroy. Before we go any further, take a moment. Think about the last time your electricity went out. Maybe a storm knocked a line down. Maybe a local transformer failed. Even that small, temporary outage probably disrupted more of your life than you expected. Your phone charger stopped. The refrigerator went quiet. If it happened at night, the darkness felt immediate and complete. And that was one small local failure, in peacetime, quickly fixed. Now multiply that. Multiply it across a city of 8 million people. Put that city under sustained aerial bombardment for 57 consecutive nights. Add rationing, fear, disrupted supply chains, exhausted workers, and a government trying to fight a war on every front simultaneously. Then ask yourself how any of it continued to function at all. The answer is more interesting than you might expect. And it starts long before the first bomb fell. There is a tendency, when we talk about the Second World War, to speak in terms of battles and borders, of soldiers and strategy, of the large movements of history that are easy to see from a distance. What gets spoken about less often is the invisible infrastructure that made everything possible on the home front. The electricity that powered the factories building the aircraft. The current running through the hospitals treating the wounded. The light that allowed night shift workers to keep producing ammunition at 2 in the morning. These things did not fight the war in any visible way. But without them, the war could not have been fought at all. Britain understood this, at least partly, before the war began. And Germany understood it too. Which is why, when the Luftwaffe began its sustained campaign against British cities in the autumn of 1940, power stations and electrical infrastructure were not incidental targets, they were deliberate ones. The remarkable thing is not that they were targeted. The remarkable thing is how consistently they survived. To understand why, you have to go back about 15 years before the war. Back to a Britain that was, in terms of its electricity supply, a patchwork of competing local systems that barely spoke to one another. In the early 1920s, if you wanted to understand the state of British electricity, you would have found something close to organized chaos. Hundreds of separate electricity undertakings operated across the country, each with its own generating equipment, its own voltages, its own frequencies, its own business model. A town in Lancashire might run its grid at one frequency, a neighboring town might run at another. The equipment was often incompatible. If one area had surplus power and another had a shortage, there was frequently no practical way to share it, because the two systems had never been designed to connect. This was not unusual for the time. Electricity supply in most industrializing countries had grown up organically, with private companies and municipal authorities, each building what they needed when they needed it, without much thought for what the system would look like at a national scale. The result, by the 1920s, was a fragmented, inefficient, and frankly embarrassing situation for a country that still considered itself the most advanced industrial nation on Earth. The man who looked at all of this and decided something had to be done was Charles Mertz, an electrical engineer whose firm had spent decades building power infrastructure across Britain and the British Empire. Mertz had a clear-eyed view of what the fragmentary system was costing the country in inefficiency, and he had been arguing for some form of national coordination for years. His ideas helped shape a government inquiry in the mid-1920s that would ultimately lead to one of the most consequential pieces of civil engineering in British history. In 1926, the British government passed the Electricity Supply Act. It created the Central Electricity Board, a public body with a specific and ambitious mandate: to build a national transmission network that would connect the best and most efficient power stations in Britain into a single, coordinated system. This network would eventually be called the National Grid. What the engineers who designed it could not have known, and what history would later make clear, was that the design principles they chose for economic reasons would turn out to be exactly the right principles for survival under bombardment. The Central Electricity Board did not try to nationalize every power station in Britain. That would have been politically impossible and practically unnecessary. Instead, it chose a more elegant approach. It identified the most efficient generating stations, the ones capable of producing electricity at the lowest cost per unit, and it connected them to a new high-voltage transmission network that ran across the country. Power could then flow from wherever it was being generated most efficiently to wherever it was most needed, crossing regional boundaries that had previously been insurmountable. The key technical decision was the voltage at which this national transmission network would operate. The engineers chose 132,000 volts, or 132 kilovolts, as the standard transmission voltage for the new grid. This was a high voltage for the era, which meant the network could carry large amounts of power over long distances with relatively low losses. Transformers at each end would step the voltage up for transmission and back down for local distribution. It was a system built for efficiency, but it was also, almost as a side effect, a system built with significant redundancy. Redundancy is the word that matters here. In engineering, redundancy means that the system has more capacity, more pathways, more backup options than it strictly needs under normal conditions. The national grid was designed with multiple transmission routes between regions. If one line went down for maintenance, power could be rerouted. If one station was offline for repairs, another could pick up the load. The system was not designed to be indestructible. It was designed to be flexible. And flexibility, it would turn out, is a very useful quality when someone is trying to bomb you into the dark. The grid was substantially complete by the mid-1930s. It had taken the better part of a decade to build. Hundreds of miles of high-voltage transmission lines crossed the British landscape on towers that, at the time, seemed almost futuristically enormous. Regional control centers were established to manage the flow of power across the network. Switching stations and substations connected the national transmission grid to local distribution networks. By the time war broke out in September 1939, Britain had an electrical system that was, by the standards of the day, genuinely impressive. Not perfect, not invulnerable, but far more capable of absorbing damage and continuing to function than almost anyone had anticipated. The war came gradually to the home front. The first year of the conflict, the period the British would remember as the Phoney War, produced relatively little direct damage to civilian infrastructure. The real test came in the summer and autumn of 1940, when the Luftwaffe, having failed to destroy the Royal Air Force in the Battle of Britain, shifted its strategy. Rather than trying to win air superiority before an invasion, Germany's air campaign turned toward attrition. The goal became the systematic destruction of Britain's industrial and civilian infrastructure, the disruption of war production, and the breaking of civilian morale. The Blitz, as it came to be known, began in earnest on the 7th of September, 1940. That evening, a force of over 300 German bombers, escorted by fighters, crossed the English Channel and headed for London. They bombed the docks in the East End of London for hours. They started fires that could be seen from across the city. When they left, they had killed over 400 people and injured many more. And the following night, they came back. And the night after that. For the next 57 consecutive nights, London was bombed. After London, the campaign spread to other cities: Coventry, Birmingham, Liverpool, Plymouth, Bristol, Glasgow, Southampton, Sheffield. Between September 1940 and May 1941, the Luftwaffe dropped tens of thousands of tons of high explosive and incendiary bombs on British cities. The scale of destruction was immense. Hundreds of thousands of homes were damaged or destroyed. Civilian casualties ran into the tens of thousands. And through almost all of it, the electrical grid kept functioning. Not without damage, not without crisis, not without nights when control room operators sat in front of their instruments watching sections of the network drop away and wondering if this would be the night the system finally broke. But it kept functioning, and that was, in the most direct sense, a matter of survival. To understand what the bombing was actually doing to the electrical system, you have to think about what a power grid actually consists of. It is easy to think of electricity as something that simply exists, like air, flowing invisibly through the world. In reality, at every moment, it is being produced and consumed simultaneously across a vast interconnected system, balanced in real time, managed by human decisions and automatic mechanisms working in concert. A power grid has several distinct layers. At the top are the generating stations, the facilities that actually produce electricity. In Britain at this time, these were almost exclusively coal-fired steam plants, burning millions of tons of coal each year to produce steam that drove turbines, that drove generators, that produced alternating current. These stations ranged in size from relatively modest local facilities to enormous installations like Battersea Power Station on the south bank of the Thames in London, which was, at the time of the war, one of the most powerful generating stations in the world. Below the generating stations is the transmission network, the high-voltage lines and cables that carry electricity over long distances. Below that is the distribution network, a more local system of lower-voltage cables, transformers, and substations that takes the electricity from the transmission grid and delivers it to homes, factories, and businesses. A bomber targeting the electrical system has several options. It can attack the generating stations, the source of the power. It can attack the transmission lines and the substations where high voltage is transformed down for local use. Or it can attack the distribution network, the local infrastructure that actually delivers power to individual buildings. Each type of attack has different consequences and different implications for repair. Generating stations are large, they are fixed, they require constant coal supply, and they are staffed around the clock. They are also, in many ways, the most valuable targets because destroying a major generating station removes a large quantity of generating capacity from the system in a single strike. But they are also, by virtue of being large industrial buildings full of massive machinery, surprisingly resilient to anything less than a direct hit on critical equipment. A near miss might blow out windows, damage roof structures, destroy outbuildings. But the turbines, the boilers, the generators themselves are heavy, robust pieces of industrial machinery that can often survive considerable blast effects. Transmission lines are, in one sense, easier to destroy. A bomb landing near a high-voltage tower can bring the tower down. But transmission lines are also easier to repair than generating stations. A fallen tower can be replaced. A broken cable can be joined. And the national grid, with its multiple parallel transmission routes, could often reroute power around a damaged section within hours. It was the substations and local distribution infrastructure that proved most problematic. These facilities, scattered throughout cities and suburbs, were harder to protect, harder to monitor, and in some ways harder to repair quickly. A damaged substation could leave entire neighborhoods without power, not because the generating capacity was gone, but because the local pathway for delivering power had been severed. This distinction mattered enormously during the Blitz, and it was understood, with increasing clarity, by the engineers running the grid. By the autumn of 1940, the Central Electricity Board had been thinking seriously about wartime resilience for at least 2 years. The possibility of aerial bombardment had been taken seriously by British military planners since the mid-1930s, and some precautionary measures had been put in place before the war began. Generating stations had received some degree of additional protection. Dispersal plans had been considered. Spare equipment, including spare transformers and switching gear, had been stock-listed at strategic locations. But no amount of preparation could fully anticipate what it actually felt like to manage a national power grid under sustained attack. The reality, when it arrived, was more demanding, more chaotic, and more dependent on individual human judgment than any planning document had captured. The men and women who worked in Britain's grid control centers during the Blitz operated under conditions that are difficult to fully appreciate from a distance of more than 80 years. These control rooms, typically located in purpose-built facilities away from the most obvious targets, were the nerve centers of the regional electricity networks. At any given moment, operators could see the status of generating stations across their region, the flows of power on major transmission routes, the demand being drawn by industrial and domestic consumers. They could issue instructions to station operators. They could open and close connections in the network, and they could make decisions about where to direct power when some part of the system was under strain. During an air raid, these decisions became urgent in a way that peacetime grid operation rarely requires. A transmission line goes down. A substation loses power. A generating station reports bomb damage and begins an emergency shutdown. The control room operator must assess the situation, identify where else in the system there is capacity, and redirect power before the imbalance in the network causes a cascade of failures that could take down far more of the grid than the original bomb damage. This is harder than it sounds. Electricity grids are sensitive systems. They operate at a fixed frequency, in Britain's case, 50 cycles per second. And if that frequency drops because too much demand is being drawn against too little generation, the system can become unstable. Generators can trip offline automatically to protect themselves. And once a large number of generators trip, the resulting sudden reduction in supply can cause a cascade that takes down the entire grid in minutes. This is what engineers call a blackout in the technical sense, not the wartime dimming of lights for air raid purposes, but a complete and uncontrolled collapse of the electrical system. The control room operators during the Blitz were constantly working to prevent exactly this. They were doing it with less information than they would have liked, in conditions that included the sound of bombs falling outside, with telephone lines that were sometimes damaged or overloaded, and with a clear understanding that the decisions they were making were not abstract engineering problems. They were decisions that affected hospitals running on grid power, factories producing aircraft components, and the people in the streets outside who had already been through enough. What kept them going, by almost every account that survives, was a combination of professional training, the particular British tendency to treat a crisis as a problem to be solved rather than a catastrophe to be endured, and something harder to quantify, the sense that the system was, despite everything, holding together, that it had more capacity than was being destroyed, that the margin was tight but real. The coal was a problem that rarely makes it into popular histories of the Blitz, but it was a constant, grinding concern for everyone responsible for keeping electricity flowing. British power stations of the 1940s ran on coal. Coal was the fuel that produced the steam that drove the turbines that generated the electricity. And coal did not appear at power stations by itself. It arrived by ship at coastal ports, by barge along canals, by wagon along roads, and most importantly, by rail. The railway network was the circulatory system of Britain's coal supply, and it was also a major target of the Luftwaffe. When railway lines were bombed, coal deliveries were disrupted. When a key marshalling yard or railway bridge was hit, trains that would normally carry coal to a generating station might be delayed by hours or days. The generating stations had fuel stockpiles, coal yards where they maintained a reserve supply, but those stockpiles were not infinite. A major station with a large generating capacity could consume a remarkable quantity of coal every day, and if deliveries were disrupted for long enough, the stockpile would begin to run down. The men who managed coal supply for Britain's power stations during the Blitz became expert at improvisation. Alternative routes were identified. Road haulage was used where rail was unavailable. Priorities were established, with military and war production facilities at the top of the list, domestic consumers further down. There were moments during the worst periods of the Blitz when the margin between a functioning grid and a fuel-starved collapse was genuinely uncomfortable. But the margin held, partly because of planning, partly because of the distributed nature of the coal supply chain, and partly because of the extraordinary efforts of people whose names never appeared in any newspaper. There is a quality to the accounts that survive from the people who kept Britain's electricity running during the Blitz that is worth pausing on. These are not stories of heroism in the theatrical sense. Nobody charged a machine gun nest. Nobody flew a fighter plane into a formation of bombers. What they did was, in some ways, quieter and stranger than that. They drove vans through bombed streets toward fires they could see on the horizon. They climbed electricity poles in the dark, while fires burned nearby because a cable had gone down and needed to be repaired before morning. They sat in control rooms and made technical decisions under conditions that would have been considered unconscionable stress in any peacetime environment. One quality that appears consistently in contemporary accounts is the matter-of-factness with which ordinary workers and engineers described what they were doing. There was not, in general, a great deal of heroic language. The job needed doing, so it was done. A line worker whose shift happened to coincide with an air raid was not given special dispensation to stay home. A control room operator whose city was being bombed around them did not leave their post. The work continued because the consequences of stopping were too clear and too immediate. If the power went off and could not be restored, the factory making aircraft components would stop. The hospital would lose its lights. The pump keeping a flooded air raid shelter dry would fail. These connections were not abstract to the people making them. They were immediate and personal. And they are one reason why, across a campaign of sustained aerial bombardment that lasted the better part of a year, the people responsible for the electrical grid continued to do what they were paid to do with a reliability that still commands quiet respect. The geography of the power grid also helped in ways that are not immediately obvious. Britain is not a large country, but it is not a uniform one either. The generating capacity of the national grid was distributed across many locations, from Scotland in the north to the south coast of England. Major stations were spread across the Midlands, along river valleys where cooling water was available, near coalfields in Wales, Yorkshire, and Northumberland. This distribution was not a deliberate wartime precaution. It reflected the geography of coal production and water supply and industrial demand that had shaped where power stations were built over the previous half-century. But it meant that no single air raid, however large, could destroy a significant fraction of Britain's total generating capacity. The Luftwaffe could bomb London extensively and knock out local distribution in parts of the city. It could damage a generating station on the Thames. But while it was doing that, stations in the Midlands and in northern England were unaffected, continuing to produce power, feeding it into the national grid, available to be redirected to where it was needed. This is the nature of a genuinely interconnected system. The same interconnection that makes it efficient in peacetime makes it resilient in crisis. Destroy one part, and the rest continues. Reroute through an alternative pathway, and the system adapts. The engineers who built Britain's national grid in the late 1920s and early 1930s built it this way for economic reasons to allow efficient sharing of generating capacity across regions. But the resilience was built in all the same. It was, in the most literal sense, a system that was more than the sum of its parts. By the time part one of this story ends, the bombs are still falling. The first night of the Blitz is barely behind us. The worst attacks on Coventry, Birmingham, Liverpool, and the other great provincial cities have not yet come. The engineers in the control rooms have not yet faced the moments when sections of the grid they were responsible for seemed to be going dark faster than they could restore them. The coal supply chain has not yet been tested to its absolute limit. The question of what happens when a major generating station takes a direct hit has not yet been fully answered. But the structure of what would happen is already there, in the design of the system itself. The redundancy, the flexibility, the distributed nature of the generation, the high-voltage transmission network with its multiple parallel routes, the regional control centers with their trained operators, the stockpiles of spare equipment, the workforce that, as yet, had not been fully tested, but which was about to be. The next question is not whether the system was strong enough to survive. The history tells us it was. The next question is how. How specifically did it continue to function when individual stations were damaged? How did the control room operators manage the real-time crises that unfolded every night? How did the coal continue to arrive when the railways were being bombed? How did cables get repaired in the dark, in the middle of air raids, fast enough to matter? Those answers are where the real story lives. There is a particular kind of darkness that people who lived through the Blitz described in ways that are hard to fully imagine now. It was not simply the absence of light. It was layered. There was the official darkness, the blackout, enforced by law and by air raid wardens, who would knock on your door if a sliver of light escaped your curtains. There was the darkness of the streets, where vehicles moved with headlights reduced to narrow slits, and pedestrians walked by memory as much as sight. And then, on the worst nights, there was a third kind of darkness, the sudden, unexpected darkness of a neighborhood that had lost its electricity, where even the dim glow behind curtained windows went out all at once, and the only light left was the orange fire of something burning in the distance. It is that third darkness that this part of the story is about. Not the controlled darkness of the blackout, which was deliberate and managed, but the uncontrolled darkness of infrastructure failure, which was neither deliberate nor managed, and which the people responsible for Britain's electrical system spent the entire Blitz trying to prevent, contain, and reverse as quickly as humanly possible. What they were fighting against was not simply the destruction of equipment. They were fighting against the logic of cascading failure, the tendency of complex systems, once they begin to break down faster than they can be repaired. Understanding how they held that tendency at bay is the core of this part of the story. The first thing to understand about how the grid failed during a bombing raid is that it rarely failed in the way people might assume. The image most people carry of wartime infrastructure damage is dramatic and visible. A bomb falls directly on a power station. The building collapses. The generators are destroyed, and the electricity stops. That happened. But it was not the most common way that power was lost during the Blitz. The more common failure was subtler, and in some ways more insidious. A bomb would fall not on the generating station itself, but in its vicinity. The blast would damage the switchgear, the equipment that controls the electrical connections between a station and the grid. Or it would rupture the oil cooling systems of a transformer, causing the transformer to overheat and shut down automatically. Or it would damage the cables feeding into a substation, leaving the substation physically intact, but electrically isolated from the generating source. Or it would start a fire in a building adjacent to a substation, and the heat would damage the insulation on the cables inside. These failures were partial and localized. They were also, from the perspective of the people trying to manage them, deeply frustrating, because the equipment still existed. The power station was still there. The substation was still there. But some critical component in the chain between them had been damaged or destroyed, and until it was repaired or bypassed, the electricity could not flow. This distinction shaped everything about how the grid was managed during the Blitz. The objective was not simply to protect generating capacity, though that mattered enormously. The objective was to maintain the pathways through which generated power could reach the places that needed it. and maintaining those pathways, particularly in the local distribution networks inside bombed cities, required a type of rapid, flexible, dangerous repair work that has rarely been written about in the way it deserves. The people who did this work were called various things at various times. Some were employees of the Central Electricity Board, responsible for the national transmission network. Others worked for the local electricity undertakings, the regional and municipal suppliers responsible for distributing power to homes and businesses within their areas. Still others were from the generating stations themselves, responsible for keeping the plant running and for managing the connection to the grid. What they shared by the autumn of 1940 was a set of procedures and protocols that had been developed in the months before the Blitz began, during a period when it was clear that bombing was coming, but the actual experience of it was still theoretical. These procedures covered things like how to respond when a section of cable was damaged, how to isolate a faulted section of the network without taking down more of the grid than necessary, how to establish temporary connections using mobile equipment, and how to prioritize which repairs to make first when multiple failures were happening simultaneously. These were not complex plans in the bureaucratic sense. They were practical guides to managing chaos, developed by engineers who had thought hard about what bombing would actually do to their systems and who had tried to prepare their teams accordingly. And when the bombing started, the teams discovered that the preparation had been, on the whole, remarkably useful, even if no plan survived contact with the reality of a city under air attack entirely intact. The repair crews that went out during and after raids were operating under conditions that require a moment of genuine consideration. They were driving through streets where bombs were still falling, or had recently fallen, where unexploded bombs might be lying in the road, where fires were burning in buildings on either side, where the road surface might have been disrupted by the blast of a nearby explosion. They were doing this in the dark, under blackout conditions, with headlights reduced to the barest minimum. When they reached the site of a cable or substation failure, they worked by the light of shielded torches, keeping the light directed downward and away from any direction that might be visible from the air. If an air raid was still in progress, which was frequently the case, they worked with the sound of anti-aircraft fire and the crump of distant bombs as a constant background. They worked quickly, because every minute of outage was a minute that a hospital might be operating without reliable light, or a factory might have its production line halted, or an air raid shelter's pumping equipment might be failing. The speed of repair was, in many cases, genuinely extraordinary. There are documented instances during the Blitz of major cable faults being located and repaired within 3 or 4 hours of first being reported, including in conditions of active air attack. This was possible partly because of the preparation that had been done, the spare equipment stockpiled, the trained crews kept on standby, the repair procedures established in advance. But it was also possible because of something less tangible, a workforce that had collectively decided, without any particular ceremony or announcement, that keeping the power on was what they were there to do, and that they were going to do it. One of the things that made rapid repair possible was a decision that the Central Electricity Board had made before the war, almost as an afterthought to its main operational planning. It had begun stockpiling key components at strategic locations around the country. The logic was simple. If a transformer or a section of cable or a piece of switchgear was damaged, the fastest repair would be one that involved swapping out the damaged component for a pre-positioned spare rather than waiting for one to be manufactured and delivered. Transformers were particularly important here because they were one of the most vulnerable components in the system, and also one of the most difficult to replace quickly. A large power transformer is not something that can be manufactured in a week. In the late 1930s, producing a major transmission transformer could take months. The Central Electricity Board recognized this and began, in the years before the war, to accumulate a reserve stock of transformers of various sizes, held at strategic locations where they could be moved relatively quickly to wherever they were needed. This was not a dramatic or exciting form of preparedness. It did not feature in newsreels or government announcements. It was simply careful engineering administration, the kind of unglamorous foresight that saves systems when everything else is going wrong. And during the Blitz, it was exactly the right kind of preparation to have made. When a substation transformer was damaged by blast or fire, the ability to bring in a replacement unit from a reserve stock, truck it to the site, and have a team of engineers install it within 24 to 48 hours was the difference between a localized outage that lasted a day and one that lasted weeks. Mobile substations were another innovation that proved its worth under wartime conditions. These were transformer and switching units mounted on heavy road vehicles, capable of being driven to a location where the fixed substation had been damaged and connecting into the local distribution network to restore power while permanent repairs were made. They were not a wartime invention. Versions of mobile electrical equipment had existed before the war, but the war created a demand for them and an urgency around their deployment that drove rapid improvement in both their capability and the procedures for using them. While the repair crews worked in the streets and the control room operators managed the moment-to-moment balance of the grid, there was a parallel problem being addressed at a level above both of them. And that was the question of how to keep generating capacity intact and available. The generating stations were not passive facilities waiting to see whether they would be hit or not. By 1940, they had become active participants in their own defense. The larger stations, particularly those in or near major cities, had received some degree of physical protection before the war began. Sandbag walls had been erected around critical equipment. Blast walls had been constructed to protect control rooms and switchgear buildings. Some stations had installed duplicate sets of critical equipment so that if one was damaged, the other could take over without a prolonged outage. But physical hardening can only do so much. A large power station is, fundamentally, a very large building full of very heavy machinery. It cannot be hidden. It cannot be moved. It sits in one place and continues to operate. And if a bomb lands in exactly the right, or rather exactly the wrong, place, significant damage will result regardless of what protection has been provided. What the generating stations could do, and did do, was develop rapid response procedures for managing damage when it occurred. When a bomb fell on or near a station, the response was not simply to assess the damage and begin repairs at a normal working pace. It was to establish immediately which generating units were still operational and capable of continuing to produce. Isolate the damaged sections from the rest of the plant as quickly as possible. Inform the grid control room of the changed generating capacity available, and begin emergency repairs on any damaged equipment that could be restored to service. This required, above everything else, trained staff who were calm under pressure and who knew precisely what to do without being told step by step. The senior engineers at Britain's major power stations were, for the most part, exactly this kind of person. They had spent years managing the complex machinery of a large generating facility. They were accustomed to equipment failures, to the kind of rapid diagnosis and repair that keeping a steam plant running requires even in normal conditions. The additional stress of an air raid was real and significant, but the basic professional competence was already there. There are accounts from Battersea Power Station, one of the most prominent and most frequently targeted generating facilities in London, of staff continuing to manage the plant through air raids that were close enough that blast effects were felt inside the buildings. Windows broken by concussion, dust falling from the ceiling, the ground vibrating with each nearby explosion. The turbines kept turning. The generators kept producing. The power kept flowing into the grid. Because stopping was not an option that the people responsible for the station were willing to consider unless a bomb had actually disabled the machinery. The control rooms deserve more attention than they typically receive in accounts of wartime Britain. These facilities were the real-time management centers of the electrical system, and the people who worked in them were operating at a level of cognitive complexity and stress that is difficult to fully convey. A regional grid control room in Britain during the Blitz would have been a relatively modest physical space by modern standards. A large room with boards or displays showing the status of generating stations and major transmission routes across the region. Telephones connecting the control room to individual stations, substations, and repair crews. A small number of operators, sometimes just 2 or 3 on a night shift, responsible for the entire regional network. During an air raid, the information arriving in the control room was fragmentary, delayed, and sometimes contradictory. A substation operator might call to report that their facility had lost incoming supply. A generating station might report that one of its generating units had tripped offline following a near miss. A field crew might report that they had found a damaged cable, but could not yet assess whether it could be repaired in place or would require a temporary bypass. All of this information was arriving simultaneously, by telephone, against a background of noise and tension, while the control room operators were also watching their instruments for signs that the network balance was shifting in dangerous directions. The decisions they made in these moments were not made with perfect information. They were made with the best information available, under significant time pressure, with a clear understanding that the wrong decision could make things considerably worse. Opening the wrong switching connection in the network, for example, could direct power toward a faulted section of cable and cause further damage, or could overload a transmission line and trip it offline, which would then require its own corrective action. The fact that these decisions were, by all available evidence, generally made correctly reflects both the quality of the training that control room operators had received and the quality of the people doing the job. These were not people who had been assigned to the control room because nothing better was available. They were experienced electrical engineers who had been placed in these roles precisely because they had the technical knowledge and the personal steadiness to manage the system under pressure. What also helped, quietly and in ways that were not always formally acknowledged, was the culture of the organizations they worked for. The Central Electricity Board and the regional electricity undertakings were, by the standards of the time, professionally well-run organizations with a genuine commitment to operational excellence. The people who worked for them had internalized the idea that keeping the supply on was not simply a job, but a responsibility. This is the kind of organizational culture that is hard to build deliberately and easy to destroy accidentally. And it is one of the underappreciated reasons why Britain's electrical system functioned as well as it did during the worst months of the Blitz. Coventry stands as the single most testing episode for Britain's electrical infrastructure during the entire Blitz. The raid on Coventry on the night of the 14th of November, 1940, was one of the most concentrated aerial attacks on a British city during the entire war. The Luftwaffe deployed over 500 aircraft. They dropped an enormous quantity of high explosive and incendiary bombs in a relatively compact target area. The city center was largely destroyed. The medieval cathedral burned. Somewhere between 500 and 600 people were killed in a single night. Coventry was also one of the most important centers of British war production. Its factories produced aircraft engines, vehicles, machine tools, and weapons of almost every kind. The electricity supply to Coventry's industrial base was not a peripheral concern. It was a critical strategic resource. The bombing did substantial damage to Coventry's electrical infrastructure. Substations were hit. Local distribution cables were severed. The local supply system was, in parts of the city, severely disrupted. The question, in the days that followed, was how quickly it could be restored, not because the people of Coventry needed their domestic lights back, though that mattered too, but because the factories needed to resume production as quickly as possible. The answer, which surprised some observers and reassured others, was faster than anyone had a right to expect. Emergency repair teams from across the region converged on Coventry. Mobile substations were brought in to restore supply to priority facilities. The regional grid control room managed the rerouting of power around the damaged sections of the local network. Within a matter of days, the most critical industrial consumers had their electricity supply restored. Within a couple of weeks, the domestic supply to most of the city had been substantially recovered. This was not a painless or easy process. The repair crews worked in a city that was still in shock, where streets were blocked by rubble, where the infrastructure of daily life had been severely disrupted, where the smell of burning was still in the air. But the electrical system's recovery was faster than its physical destruction might have led anyone to predict, precisely because of the combination of regional interconnection, pre-positioned spare equipment, trained repair teams, and effective control room management that had been put in place before the crisis arrived. Liverpool's experience during the Blitz added another dimension to the story, one that involved the relationship between the electrical grid and the port. Liverpool was Britain's most important Atlantic port, the gateway through which the supplies, food, weapons, and raw materials on which the country's survival depended flowed in from North America and elsewhere. The port was an obvious target for the Luftwaffe, and it was bombed extensively during the spring of 1941. The port could not function without electricity. The cranes that unloaded ships from their berths, the conveyor systems that moved cargo, the pumps, the lighting, the communications equipment, all of it ran on electricity. And electricity in Liverpool came from the same regional network that served the rest of the northwest of England, a network that was being strained by bombing at the same time the port was under attack. The priority decisions made during the Liverpool raids were among the most consequential of the entire Blitz from an operational standpoint. If the port's electricity supply failed and was not quickly restored, the consequences would extend far beyond Liverpool itself. Ships waiting in the Mersey to unload would be delayed. Convoys arriving from the Atlantic would have nowhere to discharge their cargo efficiently. The supply chain that kept Britain fed and armed would develop a bottleneck at exactly the point it could least afford one. The electricity supply to the port's critical facilities was maintained, with significant effort, throughout the worst of the Liverpool raids. This required the same combination of pre-positioned equipment, rapid repair, and careful management of the regional network that had worked in Coventry and London. But it also required a specific set of decisions about which consumers would get priority if generating capacity was insufficient. decisions that were made at the control room level with a clear understanding of what the stakes were. These decisions were not comfortable to make. Directing power toward the port facilities during a period of constrained supply meant directing it away from somewhere else. Domestic consumers, less critical in the immediate military sense, bore a disproportionate share of the disruption. This was understood and accepted, at least officially, as a wartime necessity. But it created its own strains on civilian life and its own demands on the organizations managing the system. One aspect of the wartime electrical story that receives almost no attention is the role of women in Britain's electrical industry during the Blitz and throughout the war more broadly. The industry, like most technical industries of the period, had been overwhelmingly male before the war. By 1940 and 1941, with large numbers of men in the armed forces, that was changing. Women took on roles in electricity supply that they had not held before, including in control rooms, in metering and billing offices, in testing and inspection roles, and in some cases in field maintenance positions. The electrical industry's official records from the wartime period reflect a workforce that was, by the middle of the war, significantly more mixed than it had been at the start. This is not a story of sudden dramatic transformation. The barriers were real, and the resistance from some quarters was genuine. But it is a story of practical adaptation driven by necessity, and the women who filled these roles during the war did so with the same competence and commitment that characterized the workforce as a whole. Their contribution to keeping the lights on is part of the record, even if it is a part that has often been passed over in accounts that focus on the more visible and traditionally dramatic elements of the wartime story. By the spring of 1941, the most intense phase of the Blitz was drawing toward its end. Germany was preparing for the invasion of the Soviet Union, and the aerial resources required for that campaign meant that the sustained assault on British cities would have to be reduced. The final major raid of the main Blitz period, on London on the night of the 10th and 11th of May, 1941, was one of the heaviest single raids of the entire campaign. It killed almost 1,500 people and caused enormous damage across the city. But Britain's electrical grid was still standing, damaged in places, strained everywhere, held together by extraordinary effort and occasionally desperate improvisation. But standing. The question that follows naturally from this is not simply whether the grid survived. It is why the German strategy failed to achieve what its planners had intended. Was it always unlikely to succeed? Had the planners miscalculated the resilience of the system they were trying to destroy? Or had the people managing that system simply outperformed what any reasonable planning assumption would have predicted? The answer, as is so often the case with historical questions that seem to have simple answers, is more layered than either alternative suggests. And it involves looking, for a moment, at the German side of the equation. The Luftwaffe's targeting intelligence for British electrical infrastructure was, by the standards of the time, reasonably good. German planners knew where Britain's major generating stations were. They knew the general layout of the transmission network. They understood, in broad terms, the relationship between generating capacity, transmission, and the final delivery of power to industrial consumers. What they appear to have underestimated, quite significantly, was the speed and effectiveness of Britain's repair capability and the degree to which the interconnected national grid could absorb localized damage without system-wide failure. This underestimation was not irrational given what was known at the time. The conventional military wisdom about infrastructure bombing in the late 1930s and early 1940s was that destroying key nodes in a network would produce cascading failures that would bring the system down. This logic worked reasonably well when applied to simpler, more linear systems. It worked less well when applied to the British national grid, which had been designed with a degree of redundancy and interconnection that made it far more robust than a simple node and link model would suggest. The Germans were, in a sense, fighting the last war's infrastructure. Their understanding of what it would take to bring the British electrical system down was based on assumptions about how electrical systems behaved under stress that were outdated by the time the grid they were attacking had been built. That is where part 2 of this story rests. The bombs are still falling, though with diminishing intensity as the spring of 1941 advances. The repair crews are still going out every night. The control rooms are still managing the balance of a system under sustained pressure. But beneath the immediate crisis, something is becoming clear. The system is not just surviving. It is, in a quiet and unannounced way, learning, adapting, becoming better at absorbing damage with every night that passes. What that learning produced and what it meant for the longer war effort is the next part of the story. There is a particular kind of knowledge that only comes from doing something under pressure, not the knowledge you get from reading a manual or attending a training course or working through a theoretical scenario in a classroom. The knowledge that comes from actually doing the thing, in the dark, with consequences attached, and discovering in real time what works and what does not. Engineers call it operational experience. Historians sometimes call it hard-won knowledge. The people who actually lived it during the Blitz would probably have used simpler language. They would have said they learned on the job. By the winter of 1940 and into the spring of 1941, Britain's electrical industry had been learning on the job for several months. And what it had learned was changing the way the system was managed, the way repairs were organized, the way generating stations operated, and the way the national grid responded to the kind of sudden, localized, unpredictable damage that sustained aerial bombardment produces. The changes were not always dramatic. Some were small procedural adjustments, the kind of thing that sounds trivial when described, but makes an enormous practical difference when applied at scale across an entire national system. Others were more significant, involving new equipment, new organizational structures, and new ways of thinking about what electrical infrastructure resilience actually meant in practice. This accumulation of experience, this slow but steady improvement in the system's ability to absorb and recover from damage, is one of the least visible but most important parts of the wartime electrical story. It happened without fanfare. It was not announced in newspapers or celebrated in government reports. It was simply the result of a large number of competent, committed people doing their jobs in difficult circumstances and getting better at them as time went on. One of the first things the Blitz revealed about the existing system was that the pre-war approach to spare equipment stockpiling, while genuinely useful, had not fully anticipated the scale and distribution of damage that sustained bombing would produce. The reserves of transformers and switchgear and cable that had been accumulated before the war were drawn down faster than expected in the early months of the Blitz. And the logistics of getting the right piece of equipment to the right place at the right time proved more complex than planning documents had suggested. The response to this was practical and rapid. The Central Electricity Board began working more closely with British electrical manufacturers to accelerate the production of key components, particularly transformers, which remained the most critical and hardest to replace quickly. Manufacturers who had been producing transformers at a normal commercial pace were asked to increase output and to prioritize the sizes and specifications most likely to be needed for rapid wartime replacement. This required changes to production scheduling, to raw material supply, and in some cases to manufacturing processes, and it did not happen overnight. But within months, the pipeline of replacement equipment had improved significantly, and the reserve stockpiles were being replenished faster than they were being depleted. At the same time, the logistics of moving heavy electrical equipment around a country with bombed roads and disrupted railways were being systematically improved. Dedicated transport arrangements were established for moving critical electrical components as a priority. Routes were planned in advance. Drivers with the right skills and the right vehicles were identified and made available on short notice. The whole apparatus of getting a spare transformer from a regional depot to a damaged substation was treated, with increasing seriousness, as a logistical problem deserving the same kind of careful attention that military supply chain planners gave to moving ammunition to the front. This sounds straightforward, described at this distance. At the time, with everything else the country was trying to manage simultaneously, making it work required sustained effort and considerable organizational ingenuity. The mobile substation program, which had begun before the war as a modest practical tool for dealing with planned maintenance outages, expanded dramatically during the Blitz into something closer to a strategic asset. By the middle of the war, Britain had a fleet of mobile substation units that could be deployed rapidly to any location where fixed infrastructure had been damaged, providing a temporary restoration of supply while permanent repairs were carried out. These mobile units were not elegant pieces of equipment. They were heavy, awkward to maneuver in narrow bombed streets, and required significant skill to connect safely into a live distribution network. But they worked. And in a city where a fixed substation had been damaged and might take days or weeks to fully repair, having a mobile unit that could restore supply to a hospital or a factory within hours was the difference between a manageable disruption and a genuinely serious crisis. The crews who operated the mobile substations became a kind of specialist force within the electrical industry, recognized for their particular combination of technical skill and physical toughness. They were the people who went in first after a heavy raid, before the full picture of the damage was clear, driving their heavy vehicles through streets that might still be under sporadic attack, connecting equipment by torchlight in conditions that no peacetime electrical worker would ever have encountered. Their work was dangerous. There were casualties among electrical repair crews during the Blitz. People killed or injured by bombs that fell while they were working, by unexploded ordnance, by the structural collapse of buildings damaged by earlier raids. The numbers were not large in comparison with civilian casualties overall, but they were real, and they were accepted by the people doing the work as part of the cost of keeping the system running. Perhaps the most significant organizational innovation of the wartime period was the development of a more formal mutual aid system between different electricity undertakings. Before the war, the relationship between the Central Electricity Board and the regional and local electricity suppliers was primarily commercial and regulatory. The board operated the national transmission grid. The local undertakings distributed power within their areas. They worked together because the system required it, but formal arrangements for one undertaking to provide emergency assistance to another in a crisis were limited. The Blitz changed this. When a city's local electricity infrastructure was heavily damaged, the resources of that city's own electrical organization were often insufficient to mount the scale of emergency repair effort required. What was needed was the ability to draw in trained staff, specialist equipment, and management support from neighboring undertakings quickly and without complicated administrative processes. The mutual aid arrangements that developed during the Blitz were, in essence, a system for doing exactly this. An undertaking that had suffered heavy damage could call for assistance and receive, within hours, teams of engineers and linemen from other parts of the country, along with equipment, vehicles, and supplies. The receiving undertaking did not have to negotiate terms or wait for approval at each step. The arrangements had been pre-established. The call went out. The aid came. This system was not perfect. There were disputes about priorities. There were moments when the undertaking providing aid was itself under pressure and could not spare as much as was needed. There were logistical complications in moving staff and equipment across a country with disrupted transport. But the system worked well enough that it became a standard part of the response to major incidents throughout the war, and it produced something valuable that outlasted the war itself. A culture of cooperation between electricity undertakings that had previously been rather more competitive and territorial than the public interest strictly required. The coal supply chain, which had been a source of persistent anxiety from the beginning of the Blitz, was also being systematically improved during this middle period of the war. The problem had never been simply that the railways were being bombed. It was that the coal supply chain was, by its nature, a long and complex sequence of steps, each of which could fail in its own way, and the failure of any one step could propagate backwards and forwards along the chain in ways that were not always predictable. Coal started its journey at the pithead, in the mines of Yorkshire, Nottinghamshire, South Wales, or the northeast coalfields. From there it went by rail to distribution points, or in some cases directly to power stations. At the power station, it was stored in coal yards, conveyed to bunkers, and fed into the furnaces of the boilers. Every link in this chain was vulnerable in its own way. The mines could be disrupted by bombing of colliery infrastructure or by the cumulative effects of wartime labor shortages. The railways could be disrupted by direct bombing damage, by damaged bridges, by destroyed marshalling yards, by the simple overloading of a network that was trying to move military supplies, food, raw materials, and fuel simultaneously. The power station's own coal handling equipment could be damaged by blast effects. Managing this chain effectively under wartime conditions required a degree of centralized oversight that had not previously existed. The Ministry of Fuel and Power, established in 1942, took on some of this coordinating role, but the practical work of ensuring that coal moved from mines to power stations, despite the obstacles, was done by a combination of railway operators, coal merchants, power station managers, and government officials working in close and sometimes uncomfortable collaboration. What emerged, over time, was a more transparent and more actively managed supply chain than had existed before the war. Information about coal stocks at individual power stations was reported more regularly. Warning systems were established so that when a station's stocks fell below a certain level, it triggered a coordinated response to increase deliveries rather than simply waiting for the situation to deteriorate further. Alternative delivery routes were identified and tested. Road transport was brought in as a supplement to rail when specific lines were disrupted. None of this was glamorous. All of it mattered. The story of the generating stations themselves during this middle period of the war is one of sustained operation under conditions that would, in any peacetime context, have been considered grounds for significant operational modifications or even temporary shutdown. The major power stations were running continuously because the demand for electricity from war industry was not decreasing. If anything, it was increasing. New factories were being built. Existing factories were adding night shifts. The war economy was consuming electricity at rates that would have seemed extraordinary by pre-war standards, and the generating stations were expected to meet that demand regardless of what was happening in the skies above them. This placed considerable strain on plant and equipment. Power station machinery is built to be robust, but it is not built to run indefinitely without maintenance. Turbines require periodic inspection and overhaul. Boilers require cleaning and repair. Generators require servicing. Under normal operating conditions, major power station equipment would be taken offline periodically for planned maintenance, giving engineers the time to inspect, repair, and restore it to optimal condition. During the Blitz and the wider wartime period, the opportunity for this kind of planned maintenance was severely restricted. Generating units that would normally have been taken offline for a week of scheduled work were kept running because the system could not afford to lose their output. The result was that the plant was operated at higher risk of unplanned breakdown than would have been acceptable in peacetime. Engineers were aware of this, and they did what they could to maintain equipment while it was running. A more difficult and less thorough process than proper planned maintenance, but better than nothing. The skill with which Britain's power station engineers managed this tension between the imperative to keep generating and the engineering reality that machinery requires care was considerable. There were breakdowns that could have been prevented by proper maintenance and were not, because the maintenance opportunity simply did not exist. But the number of serious mechanical failures that resulted from wartime overoperation was lower than might have been expected, largely because the people responsible for the plants knew their machinery intimately and were able to identify and address developing problems before they became catastrophic. The relationship between electricity and Britain's aircraft production is worth examining in some detail, because it illustrates with particular clarity why the electrical grid's survival was not simply a matter of civilian comfort, but of direct military consequence. By 1940 and 1941, Britain was engaged in a desperate effort to produce enough aircraft to replace those lost in combat, and to expand the Royal Air Force to a size capable of prosecuting the wider war. The aircraft factories of the Midlands, the south of England, and the Northwest were working at maximum capacity, with shifts running around the clock. These factories were enormous consumers of electricity. The machine tools that shaped aircraft components, the overhead cranes that moved fuselages, the ventilation systems, the lighting, the testing equipment, all of it ran on grid electricity. A power outage at an aircraft factory was not simply an inconvenience. It was a stoppage of production that had direct consequences for the number of aircraft available to the Royal Air Force. Every hour of lost production was an aircraft component that was not machined, an airframe that was not assembled, a finished aircraft that was delivered later than planned. In a situation where the margin between what was being produced and what was being lost in combat was genuinely tight, these lost hours mattered. The electricity supply to major aircraft factories was therefore treated with particular priority by the grid operators and by the local electricity undertakings responsible for delivering it. These facilities were identified as critical consumers whose supply should be maintained or restored as quickly as possible, even at the cost of disruption to other, less critical customers. This sounds straightforward as a principle. In practice, it required constant active management because the factories were in cities that were being bombed along with everything else, and keeping their supply intact or quickly restored required exactly the kind of rapid response and priority allocation that the improved wartime management arrangements were designed to provide. There are specific documented cases where the electricity supply to aircraft production facilities was restored within hours of bombing damage to local infrastructure through the deployment of mobile substations or the rapid rerouting of supply through alternative network paths, and where this restoration directly enabled the continuation of production shifts that would otherwise have been lost. These cases do not appear in histories of the Battle of Britain or the wider air war, but they are part of the same story. The question of morale is one that comes up repeatedly in wartime accounts, and it is one that has a specific relevance to the electrical system. There is a great deal of historical discussion about what sustained civilian morale during the Blitz. The famous British Stoicism, the sense of shared adversity, the leadership of Churchill, the knowledge that the country was fighting for its survival. All of these things were real and important. What gets less attention is the role that the continued functioning of essential services played in maintaining the sense that life, while disrupted and dangerous, was still manageable. Electricity was part of this. Not because people needed electricity for luxury or comfort, though those things mattered too, but because the presence of working electricity was a signal, quiet and unannounced, that the systems of civilization were still functioning, that the bombing had not broken everything, that the country was still operating. When the lights came back on after an outage, even a brief one, the effect on the people in the affected area was disproportionate to the practical significance of the restoration. It was not just that the kettle worked again or the wireless could be switched on. It was the signal that something had been fixed, that someone had gone out in the dark and the danger and made it work again, that the disruption was temporary, not permanent. The electrical repair crews, without any intention of performing a symbolic role, were performing one. Every restored supply was a small act of defiance against the logic of the bombing campaign, which was premised on the idea that sustained destruction would eventually break the country's will to continue. The speed and consistency of the restoration told a different story. It said, in the most practical possible terms, that the damage could be repaired, that the system was resilient, that whatever the bombers destroyed tonight would be working again by morning. This was not a trivial contribution to civilian morale. It was, in a quiet way, a significant one. By the middle of 1941, the patterns that would define the rest of the wartime electrical story were firmly established. The grid had been tested by the most intensive bombing campaign it would face during the entire war and had come through it functionally intact, damaged in places, strained everywhere, but operating. The organizational improvements made during the Blitz, the mutual aid arrangements, the improved stockpiling, the mobile substation fleet, the more active coal supply management, the priority allocation procedures for critical consumers were now embedded in the way the industry operated. They had been developed under extreme pressure, and they had worked. The later stages of the war brought their own challenges. The German bombing campaign did not end in May 1941. It reduced in intensity as Germany's attention turned eastward, but it did not stop entirely. Sporadic raids continued through 41 and 1942. The V-1 flying bomb campaign that began in the summer of 1944 brought a new kind of threat to southern England, one that was geographically concentrated and produced damage patterns somewhat different from conventional bombing. The V-2 ballistic missile attacks that followed the V-1s were impossible to intercept and produced intense localized destruction wherever they fell. Each of these later phases of the air campaign presented fresh challenges to the electrical system, and each was met with the organizational capability and operational experience that the Blitz had built. The response to V-1 and V-2 damage to electrical infrastructure in southern England drew directly on the procedures, the equipment stocks, and the mutual aid arrangements that had been developed and refined during the main Blitz period of 1940 and 1941. There was, by this stage of the war, something that the electrical industry had that it had not possessed in September 1940. A deep and hard-won understanding of exactly how its system failed under bombing, exactly what repairs were needed, and exactly how to organize the response most effectively. This understanding was itself a form of resilience, less visible than a spare transformer, but in some ways just as valuable. The industrial cities of the north of England and Scotland faced their own particular challenges during the middle and later phases of the war. Glasgow, Sheffield, Manchester, Newcastle. These were cities where the electrical demand from war industry was enormous, and where the bombing, when it came, was intense enough to produce serious challenges for local supply systems. Sheffield's experience during the raids of December 1940 illustrated the particular vulnerability of an industrial city, where steel production was the dominant consumer of electricity. The Sheffield steel industry was one of the most electricity-intensive in Britain, running enormous electric arc furnaces and rolling mills that drew power at scales that dwarfed most other industrial consumers. The bombing of Sheffield in December 1940 damaged local electrical infrastructure significantly and created a supply situation that required emergency intervention from the regional grid, the rerouting of transmission-level power into the city through alternative paths, and the rapid deployment of mobile equipment to restore supply to the most critical steel production facilities. The restoration was achieved, but not without significant effort and not without periods during which some of the city's steel production was operating below capacity. The urgency of that restoration reflects how directly the electrical system's performance during the war was connected to the physical capacity to produce the material that the war required. Steel for ships, steel for tanks, steel for artillery, steel for the structural components of factories and airfields and bridges. All of it dependent, in the final analysis, on electricity flowing reliably to the furnaces and mills that produced it. This is the kind of dependency that is easy to state abstractly and easy to forget in the face of more immediately dramatic wartime narratives. But it was real, and the people managing Britain's electrical system understood it with a clarity that came from having to act on it every day. There is a figure who appears in several wartime accounts of the British electrical industry, not by name in most cases, but by role. The regional controller, the person in charge of the grid for a particular area of the country, who on the worst nights of the Blitz would spend hours on the telephone to stations and substations and repair crews across their region, managing the impossible arithmetic of too much demand and too little available generation, looking for the millimeter of margin that would keep the system stable while the repair crews worked. These people were not public figures. Their names were not known outside their industry. They did not give speeches or appear in newsreels. They sat in control rooms and solved problems, one after another, through the night, and then did it again the next night. What they were doing, in technical terms, was load management. The art of matching the electricity being generated at any given moment to the electricity being consumed in real time across a complex interconnected network. In normal conditions, this is a demanding but manageable task. Under wartime conditions, with generating capacity being disrupted unpredictably by bombing and demand from war industry remaining high and relatively inflexible, it required a level of skill and sustained concentration that goes well beyond what most technical roles ask of the people performing them. The fact that the system did not, during the entire Blitz and the subsequent phases of the air campaign, experience a complete and uncontrolled collapse of the kind that engineers feared was possible is a tribute to many things. To the design of the grid, to the stockpiles of spare equipment, to the repair crews, to the coal supply chain. But it is also, and not least, a tribute to those controllers sitting in their rooms, watching their instruments, answering their telephones, making their decisions, keeping the balance. As the autumn of 1941 gave way to winter, and the immediate crisis of the main Blitz receded into a new kind of wartime normalcy, Britain's electrical industry began to turn some of its attention, for the first time since the war began, toward the future. The pressing operational demands of the Blitz had consumed almost all available organizational energy for the better part of a year. Now, with those demands somewhat reduced, it became possible to think about what came next. Not just about surviving the rest of the war, though that remained the dominant concern, but about what the electrical system should look like when the war was over. The experience of the Blitz had taught the industry things about its own system that it had not known, or had not known with such clarity, before. It had learned where the vulnerabilities were. It had learned what redundancy actually meant in practice, as opposed to in theory. It had learned what happened when the system was pushed beyond its designed operating parameters, and how long it could sustain that condition before something failed. It had learned, above all, that the principles on which the national grid had been built, interconnection, redundancy, centralized management with flexible regional response, were the right principles, not just for economic efficiency, but for resilience in the face of sustained disruption. These lessons would shape the design of the post-war electrical system in ways that were not always made explicit, but were deeply embedded in the thinking of the engineers and administrators who would go on to plan and build the expanded national grid of the 1950s and 1960s. The wartime grid had survived by the narrowest of margins in some of its darkest moments, and the people who had lived through those moments did not forget what they had learned. That learning, and what it produced in the years after the war, is the final part of this story. The war ended in stages, as wars often do. In Europe, the formal surrender came in May 1945, and the immediate, visceral relief of that moment has been described in enough memoirs and histories that it needs no further elaboration here. What is less often described is what came after the relief. The long, unglamorous, often frustrating work of taking a country that had spent 6 years organizing itself entirely around the requirements of survival and war production, and converting it back into something that could sustain ordinary peacetime life. For Britain's electrical industry, this transition was both simpler and more complicated than it might appear. Simpler, because the war was over and the bombers were not coming back. Complicated, because the country that emerged from the war was not the same country that had entered it. The infrastructure had been strained to its limits for 6 years. The workforce was exhausted and in some cases depleted. The equipment was worn. The generating stations that had run continuously, often beyond their designed operating parameters through the entirety of the war years, now needed the maintenance and overhaul that had been repeatedly deferred. And simultaneously, the demand for electricity was not decreasing. If anything, it was about to increase dramatically. As a country that had spent 6 years suppressing its civilian consumption began to release that suppressed demand all at once. The post-war electricity crisis in Britain is not a story that features prominently in popular histories of the period. But it was real, and it was severe, and it was directly connected to the wartime experience of the grid. The winter of 1946 to 1947 produced what is still remembered by those who lived through it as one of the worst energy crises in British history. The combination of an exceptionally cold winter, coal shortages caused by a combination of wartime disruption and post-war labor difficulties in the mines, and the accumulated underinvestment in generating and distribution infrastructure produced a situation in early 1947 where large parts of Britain experienced prolonged electricity cuts. Factories were ordered to close several days a week. Domestic consumers had their supply restricted to certain hours. The situation was genuinely dire, and it produced a political crisis that reverberated through the government of the day. The irony was not lost on people at the time. Britain had managed to keep its electrical system functioning through 57 consecutive nights of bombing during the Blitz, through years of sustained aerial attack on its cities, through V-1s and V-2s and everything the Luftwaffe could throw at it. And then, 18 months after the war ended, in peacetime, the lights went out for weeks. The explanation for this apparent paradox is less ironic than it first appears. The wartime grid had survived because of extraordinary human effort applied to a system that was, in many respects, operating beyond its sustainable limits. The effort could not be maintained indefinitely. The deferred maintenance, the worn equipment, the exhausted workforce, the coal supply chain that had been pushed and improvised and managed by force of will for 6 years. All of these accumulated stresses came due simultaneously in the immediate post-war period, at exactly the moment when the extraordinary effort that had held them at bay was no longer being demanded. The 1947 crisis was, in a real sense, the bill arriving for the wartime miracle. The grid had survived the Blitz by consuming its own reserves of resilience, and those reserves now needed to be replenished. The response to the 1947 crisis accelerated a process that had already been set in motion by the post-war Labour government. The nationalization of the electricity industry and the creation of a single, unified national organization responsible for generation and transmission across Britain. The Electricity Act of 1947 established the British Electricity Authority and a network of regional electricity boards, bringing together the patchwork of municipal and private electricity undertakings that had existed alongside the Central Electricity Board into a single nationalized structure. This was a major political and organizational change, and it was controversial in ways that belong more to the history of post-war British politics than to the story of the electrical grid itself. But from the perspective of the grid's technical development, what mattered most about nationalization was not the political principle involved, but the practical consequences for investment and planning. For the first time, the entire British electricity system, from the coal-fired boilers at the generating stations to the final delivery cables serving individual homes, was under unified management and could be planned and invested in as a single coherent system. The regional fragmentation that had limited the pre-war grid's development, and that the wartime experience had shown to be a vulnerability as well as an inefficiency, was being systematically eliminated. The engineers who took on the task of planning the post-war expansion of the grid brought with them something invaluable: direct personal experience of how the wartime grid had behaved under stress. Many of the senior figures in the new nationalized electricity industry were the same people who had managed the system during the Blitz, who had sat in the control rooms making split-second decisions as bombs fell, who had organized the repair crews and managed the mutual aid arrangements and kept the coal moving. They knew, with a precision that no theoretical analysis could have produced, exactly where the wartime grid had been strong and exactly where it had been fragile. The lessons they carried forward shaped the post-war grid in specific and traceable ways. The most important of these was the principle of interconnection, taken to a level of ambition that the pre-war grid had never achieved. The wartime experience had demonstrated, beyond any reasonable doubt, that an interconnected grid was far more resilient than a collection of separate regional systems, even if those regional systems were individually well designed. The more pathways there were through which power could flow, the harder it was to disrupt the system by damaging any single element of it. The post-war planners therefore set about dramatically expanding the transmission network. New high-voltage lines were planned and built at a pace and scale that dwarfed the original grid construction of the late 1920s and early 1930s. The voltage of the transmission network was progressively increased, first to higher levels within the existing 132 kilovolt system, and then, in the 1960s, to the 275 kilovolt and 400 kilovolt supergrid that forms the backbone of the British transmission system to this day. Higher voltages meant more power could be carried over longer distances with lower losses, and more power flowing through more routes meant more redundancy and more flexibility. The wartime lesson about the importance of redundancy was embedded in the design standards for the new grid. Where the pre-war transmission network had in some cases relied on single transmission routes between regions, the post-war network was designed so that any major route could be lost without causing a supply failure, because alternative paths existed to carry the load. This N-1 criterion, as engineers came to call it, the requirement that the system should continue to function normally, even if any single element fails, became a fundamental design principle of the post-war British grid, and it remains so today. It is, in essence, the lesson of the Blitz encoded into engineering standards. The generating stations themselves underwent a profound transformation in the post-war years. The wartime experience had made clear the vulnerability of having critical generating capacity concentrated in a small number of very large stations located near major cities. Battersea, Bankside, and the other great riverside stations of London had been obvious targets precisely because they were so large and so prominently located. The post-war planners began to think more carefully about the geographic distribution of generating capacity, favoring locations that were closer to fuel sources and further from the most obvious target areas, even though the strategic bombing context that had made this consideration so urgent was, for the moment, receding. New coal-fired generating stations were built at sites chosen for their access to coal, water for cooling, and transmission connectivity, but also with some consideration of how they would fit into the overall resilience of the system. The generating capacity added in the 1950s and 1960s was distributed across Britain in a way that reflected both economic logic and the hard-won understanding that concentration was a vulnerability. The arrival of nuclear power in the late 1950s and 1960s added a new dimension to this story. Britain's first commercial nuclear power stations, beginning with Calder Hall in 1956, were not primarily a response to wartime lessons about grid resilience. They were part of a broader technological ambition and a recognition that coal, the fuel on which the entire British electrical system had always depended, was becoming more expensive and more difficult to produce in the quantities the expanding economy required. But the addition of nuclear generating capacity to the grid did have the effect of further diversifying the fuel sources on which the system depended, reducing, at least at the margin, the vulnerability to coal supply disruption that had been such a constant concern during the Blitz. The organizational innovations of the wartime period also left lasting traces in the post-war electricity industry. The mutual aid arrangements between electricity undertakings that had been developed during the Blitz were formalized and improved in the post-war nationalized structure. The concept that a severe incident in one part of the system should trigger a coordinated response drawing on resources from across the network became a standard principle of operational planning rather than an emergency improvisation. The control room culture that had developed during the wartime years, the combination of technical precision, calm under pressure, and willingness to make consequential decisions quickly with incomplete information, became an implicit standard for the people who staffed the grid's control centers in the post-war decades. The wartime experience was not formally taught as history in the training programs of the post-war electricity industry, at least not in any systematic way. But it was present in the culture, transmitted through the professional example of the people who had lived through it, and who remained in senior positions for years afterward. This kind of cultural transmission is hard to measure and easy to overlook. But it matters. Organizations, like individuals, carry their formative experiences with them. The British electricity industry's formative experience was the Blitz, and the habits of thought and practice that the Blitz produced did not disappear when the war ended. They became part of what the organization was. The broader question of what the wartime electrical story tells us about infrastructure resilience more generally is one that engineers and planners have returned to repeatedly in the decades since the war. The British grid's survival of the Blitz has been studied, in various forms, by people interested in critical infrastructure protection, emergency management, and the design of complex systems that need to function under stress. Several themes emerge consistently from these analyses. The first is the importance of redundancy, not as a luxury to be added if the budget allows, but as a fundamental design requirement for any system that needs to continue functioning when parts of it fail. The pre-war national grid had been designed with redundancy for economic reasons, to allow efficient load sharing across regions. This economically motivated redundancy turned out to be exactly the right kind of resilience for absorbing wartime damage. The lesson is that designing for efficiency and designing for resilience are not always in tension. Sometimes, as in the case of the national grid, the most efficient design is also the most resilient one. The second theme is the importance of operational capability. The trained people, the pre-positioned equipment, the established procedures, the organizational culture that determines how a system responds when something goes wrong. The physical design of the wartime grid was necessary, but not sufficient for its survival. What made the physical design effective under bombing was the organizational capability brought to bear in managing and repairing it. A resilient design operated by an unprepared or disorganized workforce would not have produced the same results. The combination of physical resilience and organizational capability was what allowed the system to survive. The third theme is the value of learning under pressure. The British electrical industry of September 1940 was less capable of managing sustained bombing damage than the same industry of May 1941. Not because its physical infrastructure had improved dramatically in those 8 months, though some improvements had been made, but because the people running the system had learned, through direct operational experience, how the system actually behaved under stress, and had used that learning to improve their procedures, their organizational arrangements, and their equipment deployment. The willingness to learn from experience, to change what was not working and reinforce what was, is itself a form of resilience. And it was present in the wartime British electrical industry in considerable measure. The V1 and V2 campaigns of 1944 and 1945 deserve a moment of separate consideration, because they presented challenges that were in some ways different from the conventional bombing of the Blitz. The V1 flying bombs, launched from sites in northern France and the Netherlands, fell on southern England in large numbers during the summer and autumn of 1944. They were not aimed with precision. They could not be, given the technology of the time, but their sheer numbers and their random distribution across a wide area of Kent, Sussex, and London produced a pattern of damage that was geographically concentrated in a way that the Blitz had not been. The electrical infrastructure of southern England absorbed a considerable number of V1 impacts, both direct and near miss. The response drew directly on the procedures and resources that the Blitz had produced. Rapid assessment, mobile substation deployment, mutual aid from neighboring areas, priority restoration for critical consumers. The system performed well, better than it had performed during the early months of the Blitz, precisely because it now had nearly 4 years of operational experience to draw on. The V2 rockets that followed the V1s were a different kind of challenge. They arrived without warning, traveling faster than the speed of sound. And the first indication that one had been fired was the explosion when it arrived. There was no air raid warning, no opportunity to take precautionary action before impact. When a V2 fell near electrical infrastructure, the response was entirely reactive, and the speed of that reactive response was the only variable that could be managed. The electrical industry managed it with the competence that the wartime years had developed. Repair teams were at damaged sites faster than they would have been in 1940. Equipment was available and procedures were established. The system's response to V2 damage was, in operational terms, as good as it was possible to be given the nature of the weapon. The final V2 fell on Britain, 27th of March, 1945. 6 weeks later, the war in Europe was over. There is a particular kind of infrastructure that becomes visible only in its absence, and electricity is perhaps the clearest example of this phenomenon that the modern world has produced. On an ordinary day, in an ordinary city, the electrical system is completely invisible to the vast majority of the people who depend on it. The wires and cables are underground or overhead, unremarked. The substations are fenced compounds with warning signs, noticed only when you happen to walk past one. The generating stations, if they are visible at all, are landmarks in the landscape, familiar but not thought about. The control rooms might as well not exist, for all that most people know or care about them. This invisibility is, in one sense, the mark of a successful system. A system that people never notice is a system that is always working. The moment it becomes visible, something has gone wrong. During the Blitz, the electrical system became visible to millions of people who had never thought about it before. Not because they suddenly developed an interest in engineering, but because the possibility of its absence became real in a way it never had been in peacetime. The outages, even when brief and localized, reminded people that the electricity they took for granted was not simply there, like gravity or air, but was being produced and delivered by a human system, managed by human beings, vulnerable to human destructiveness, and dependent for its continued operation on human effort. This recognition, once it had occurred, was not quickly forgotten. The post-war British public had a relationship with their electrical system that was, in some ways, more informed and more appreciative than the relationship that had existed before the war. Not in a detailed technical sense. Most people still had no idea how the grid worked, but in a broader sense, an awareness that it was not invulnerable, that it required effort to maintain, and that the people who did that work were performing a service that mattered. This awareness expressed itself in various ways, some practical and some political. The public support for investment in the post-war electricity system, for the nationalization program, for the expansion of the grid, reflected in part a recognition that the wartime experience had shown what happened when the system was inadequately resourced, and that the lesson was worth taking seriously. The wartime electrical system's survival had been, in the deepest sense, a collective achievement, and the public had enough awareness of that to make it a political priority in the post-war years. The people who built and maintained Britain's wartime electrical system are, for the most part, unknown today. There are no monuments to the control room operators who kept the grid balanced through the worst nights of the Blitz. There are no national commemorations for the line crews who drove toward fires to repair cables in the dark. The electrical engineers who improvised their way through crisis after crisis, who kept the coal moving and the transformers replaced, and the mobile substations deployed, have left almost no trace in the popular memory of the war. This is not unusual. The history of infrastructure is almost always the history of invisible people doing invisible work to maintain the systems that visible history depends upon. The battles are remembered. The generals are commemorated. The political decisions are analyzed and debated. The cables and the transformers and the control rooms are forgotten, along with the people who spent the war years keeping them operational. What those people did was, in the most literal sense, keep civilization running. Not the idea of civilization, not some abstract value worth fighting for, but the physical, material, day-to-day operations of a modern society. The factories, the hospitals, the communication systems, the domestic life of millions of people who were already enduring enough. They kept the lights on. They kept the machines running. They kept the system alive. And because they did, the country could continue to do the other things it needed to do. Build aircraft, train soldiers, feed people, produce weapons, sustain the effort of a long and terrible war until the moment when the effort paid off. The national grid that exists in Britain today is, in its fundamental principles, the descendant of the system that survived the Blitz. It is vastly more capable, vastly more sophisticated in its management, vastly more interconnected than its wartime predecessor. The control rooms of the modern national grid use computational power that would have been inconceivable in 1940 to manage the real-time balance of a system far more complex than the one that existed during the war. The transmission network operates at voltages far higher than the wartime grid. The generating mix includes technologies, wind, solar, nuclear, gas, that did not exist or were not commercially available in 1940. But the underlying principles are the same: redundancy, interconnection, centralized management with flexible regional response, pre-positioned spare equipment, trained operators capable of making consequential decisions quickly with incomplete information, a culture that treats the continuity of supply as a fundamental responsibility rather than a commercial convenience. These principles were not invented during the Blitz. They were present in the design of the original national grid, built in the late 1920s and early 1930s for economic reasons that had nothing to do with war. But they were validated by the Blitz in a way that no peacetime experience could have achieved. They were tested against the worst that sustained aerial bombardment could throw at them. And they held. And because they held, they became the foundational principles of every electrical grid that Britain built afterward. The next time the lights come on when you flick a switch, the connection to this story is real, even if it is invisible. The grid that powers your home is built on design principles whose resilience was proven under fire, literally under fire, in the bombed cities of wartime Britain. The redundancy that means a fault on one part of the network does not cut your supply is the same redundancy that allowed London to maintain power when its substations were being bombed. The interconnection that allows power to flow from a wind farm in Scotland to a home in the south of England is the same interconnection that allowed the wartime grid to reroute power around damaged sections in the middle of a raid. The system remembers, even when the people have forgotten. There is a quiet satisfaction in the way this story ends, though it is not the dramatic satisfaction of a battle won or a treaty signed. It is the quieter, more durable satisfaction of a system that was built well, tested hard, and emerged from the test with its fundamental soundness confirmed. The people who built the national grid in the 1920s and 1930s were not thinking about war. They were thinking about efficiency, about reducing the waste of a fragmented electricity supply industry, about providing reliable and affordable power to the homes and factories of an industrializing nation. They were engineers and administrators solving economic problems, not military ones. That the system they built turned out to be exactly the right system for surviving sustained aerial bombardment was, in the most precise sense of the word, fortunate. But fortune is not the whole story. The design principles they chose, the interconnection, the redundancy, the centralized management, are principles that reflect a deep understanding of how complex systems fail and how they can be made resilient. Those principles are good principles for any critical infrastructure, in any era facing any kind of stress. The wartime test revealed their value with unusual clarity, but their value would have been real regardless of whether the war happened. And the people who operated the system during the war, who took those principles and made them work under the most demanding conditions imaginable, brought something to the system that its designers could not have built in: the human quality of commitment, the willingness to keep going when things are difficult, the professional discipline that keeps a person at their post when every instinct might suggest otherwise, the practical intelligence that finds a way through a problem when the planned solution is not available. These human qualities are not typically part of engineering specifications. They do not appear on circuit diagrams or in transmission capacity tables. But they are, in the end, what kept the lights on. Not just the design of the grid, not just the pre-positioned spare equipment, not just the mutual aid arrangements and the control room procedures. The people, their judgment, their commitment, their willingness to go out in the dark toward the fires and make the repairs. By morning, the lights were on, as if it had happened by itself. It never happened by itself. It never does.